The topic we'll be discussing in this lecture is operations on fuzzy sets. Okay. So in the last lecture we have discussed about different types of membership function, and also we have discussed towards the end concentration and dilation. So the topic we'll be discussing in this lecture is operations on fuzzy set. Like how we perform different operations on a normal set or a crisp set. Like we perform operations like union, intersection, complement, etc. All such operations can also be performed on fuzzy set, and how it should be done. That's what we are going to discuss in this lecture. So first let us take the operation union. How to perform, let us see how the union operation should be performed on a fuzzy set. So let us take two fuzzy sets, say A is a fuzzy set and B is a fuzzy set. And if you want to perform A union B, then it will be represented like this. That is, mu, the membership function of A union B of X, will be equal to max of the membership function of X, comma the membership, the membership function of A with X, and membership function of B. Okay. So A union B, the membership function of A union B will be equal to max of the membership function of A and the membership function of B, right? So here is an example. Let us assume that A is a fuzzy set, and the set A contains these elements x1 0.5, for x2 the membership value is 0.1, for x3 it is 0.4. This is for the fuzzy set A. Coming to the fuzzy set B, for x1 the membership value is 0.2, for x2 the membership value is 0.3, for x3 the membership value is 0.5. Now from these two fuzzy sets we are deriving a new fuzzy set called C, where C is nothing but A union B. So the rule for A union B, what it says, it should be max of the membership function of A, comma the membership function of B, right? So you take, for example, you take this x1. So out of this x1, which is having the highest value, the membership value of A is highest. Okay, this is because for A it is 0.5 and B it is 0.2. So we will take this. In this case, we will take this. So the resultant membership function for C, which is A union B, for x1 it will be x1 comma 0.5. Similarly for B, when you see the membership function for the membership value for x2 it is 0.1, whereas for B, okay, whereas for B the membership value for x2 it is 0.3. So in this case, 0.3 is bigger than 0.2, so we will take this x2 comma 0.3. Okay. Similarly, when you see for x3, the membership value for A is 0.4, and the membership value for x3 for B it is 0.5. So 0.5 is larger, so we will take x3 comma 0.5, right? So this is the resultant membership function. So this is how we perform union. That is, the union operation is nothing but max of the membership function of A and the membership function of B, right? And this can be graphically represented like this. So let us assume that this is the membership function corresponding to A. This is the membership function corresponding to A, and say this is the membership function corresponding to B. Okay. So now what is actually the concept of union? Union says that the A union B, the membership function corresponding to A union B is nothing but max of A and B, right? So from this point, for this value of x, so these are different x values, right? X say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so on and so forth. So when x is 0, so this is mu A, this is mu B. Okay. When x is 0, what is the membership value of A? So this point is 1, this is 0. Then for A it is 1 and for B it is 0. But it should take the max value, right? So it will take this one. Okay. When x is 1, what is the membership value for A? Again it is 1. For A it is 1, for B it is somewhere here. Point, point, point 2 or 0.3. So again it will take the max value, right? When x is 2, the membership value for A is 1, for B is somewhere here. So it is 0.7 or 0.8. Again it will take this one. When x is 3, the membership value for A is 1, for B it is somewhere here 0.8, so it will take zero point 0.1, it will take 1, right? Okay, when X is 4, you see the membership value corresponding to uh, say this is intersecting here. Okay, membership value corresponding to A is also this point, B is also this point, so it will take this. Okay, when so when similarly when X is 5, the membership function for B is this, for A, sorry, for A is this, the membership function corresponding to A is this point. What is this? This is 0.1 or zero point 0.2, whereas for B it is 0.8, so it will take this point. Are you getting? So basically it will take the value which are largest. Okay, so the resultant membership function, how it will be? So the resultant membership function will be something like this. Just a minute. So the resultant membership function, which is A union B, it will take only the values which are highest of the two. It will take only those values which are highest point of those two. Okay, so the resultant membership function will be something like this. It will be this. This will be the resultant membership function. Okay, and that is how we got this graph. Okay, so up to this point it is taking from the membership function A. From here onwards it is taking from membership function B, because from here onwards membership function B is giving higher result rather than A, right? So this is how union works with fuzzy sets. Okay, next we'll be discussing about intersection. So if there are two fuzzy sets A and B, then then we can derive a new fuzzy set which is A intersection B. Okay, and the membership function for A intersection B will be nothing but minimum of the membership function of A and the membership function of B, right? So if you take this same example, say this is fuzzy set A, this is fuzzy set B. A contains x1.5, x2.1, x3.4, and B contains x1.2, x2.3, and x3.5. Here with respect to x1, if you see, 0.2 is smaller. Okay, because it will take minimum. So the resultant fuzzy set, that is C, which is A intersection B, is in x1 it will take 0.2. For x2, if you see, 0.1 is smaller, so it will take it from A, so x2 comma 0.1. For x3, it is 0.4 is smaller, so it will take x3 comma 0.4, right? And this is the graphical representation. So now we should take minimum. So this is the membership function for A, this is the membership function for B. Now if you take the minimum out of this 2 point, which is minimum, this is minimum. So always you should take minimum. So the resultant graph will be this. Okay, so that is how we got this graph, right? So this is how the intersection of fuzzy sets were done. Complement. So complement of a fuzzy set A is given like this. So the resultant membership function uh, for a complement of a fuzzy set A will be 1 minus the membership function of A. Okay, it is just 1 minus the membership function of A. So if you have a membership, if you have a fuzzy set A with these membership values, that is for x1 it is 0.5, for x2 it is 0.1, for x3 it is 0.4, then then the membership function C, which is nothing but A complement, will be x1 comma 0.5. How we got this 0.5? It is nothing but 1 minus it is 1 minus the membership value of A. So 1 minus 0.5 is 0.5, right? And x2 it is 1 minus 0.1 is 0.9. For x3 it is 1 minus 0.4 is 0.6. Okay, so it is just inverse 1 minus of that. Okay, so this is the membership function corresponding to, if this is the membership function corresponding to A, then what will be the membership function corresponding to A complement? Okay, or A dash. A complement can also be called as A dash. Okay, A dash or A complement, what it will be? It will be 1 minus this. See, if this point, say this is 1 and this is 0, then this is 1, 1 minus 1 is 0, so this will be here. Okay, so all these points will be 0. Okay, say this point is 0.8. If this is 0.8, then 1 minus 0.8 will be 0.2, so we'll get somewhere here. Okay, say this point is uh, 0.7, then 1 minus 0.7 is 0.3, so you'll get somewhere here, right? So on and so forth. Okay, so if this point is 0.5, then 1 minus 0.5 is 0.5, so you'll get here. Okay, if this point is zero point 0.6, then you will get 1 minus, see this point is zero point 0.4, then you will get 1 minus 0.4, zero point 0.6, so you will get somewhere here. So the resultant graph will be something like this, right? So this is the membership function corresponding to A, and the membership function corresponding to A complement will be like this, right? So that we got this graph. So this is the graph corresponding to A complement, whereas this is the one corresponding to A, right? So next, the other operations that can be performed on a fuzzy set are like vector product and scalar product. Vector product is otherwise called as algebraic product. It is also called as algebraic product. So the algebraic product of two fuzzy set A and B can be represented like this. That is the resultant membership function of A dot B of X will be equal to the membership function of A dot in the sense it is normal multiplication multiplied by the membership function of B. That's it. Okay. Say for example, A is something like this. X1 comma 0.3, okay, and x2 comma 0.2, okay. Say B is x1 comma 0.5, okay, this is x1 comma 0.5 and x2 comma 0.8. So this is the membership function. Then the resultant membership function C, which is nothing but A dot B, will be it will be just the vector product of these two. So what is 0.3 into 0.5? So 0.3 into 0.5 is 0.15, right? Yes. So it will be, so x1 it will be 0.15, okay. X1 it will be 0.15, okay, and 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 x2 will be 0.16, right? 0.8 into 0.2, right? So it will be 0.16. So x2 comma 0.16. So this will be the resultant membership function. So this is how the dot product work, right? Whereas scalar product, now in the vector product, both are vectors. A and B are vector. I mean both are fuzzy set. A is also a fuzzy set, B is also a fuzzy set, and a fuzzy set is a vector. Okay, because each element contains two entities, right? It is ordered pair, right? Whereas in scalar product, you multiply a scalar value with one fuzzy set, right? So let us take A alone. Okay, with A alone, if I want to multiply some scalar value, say alpha is equal to point 2, if I want to multiply, then mu alpha A of x will be what? It will be it will be x1 comma zero point 0.3 into zero point 0.2. What is 0.3 into zero point 0.2? It is 0.006, right? 0.3 into zero point 0.2 will be 0.06. So x1 will be 0.06, and what will be x2? X2 will be 0.2 into zero point 0.2, that is 0.04, right? So here we are just multiplying a scalar value, whereas in this vector product we are taking two vectors and we are multiplying, right? So that's the difference. So this is how the scalar and the vector dot products works in case of fuzzy set operations, right? So next, similarly, there are other operations. Sum of two fuzzy sets A and B can be represented like this. Sum of two fuzzy sets A and B. That is sum of A plus B. The resultant fuzzy set will produce a membership function of A plus B of X, which is equal to the membership function of A plus the membership function of B minus the membership function of A dot B. Okay, so it is not just A plus B. The membership function of A plus B minus the membership function of A dot B. Okay, so first you have to calculate A dot B. That is the dot product of two vectors you have to calculate, and that should be subtracted. Then you have to calculate the addition of two membership function, and that should be subtracted with this. Right? That is what you have to do. Okay. Similarly, difference A minus B, the membership function A minus B is given like this. A minus B is nothing but A intersection B complement. Okay. So the membership function, if you want to calculate the difference between two fuzzy set A and B. So that is nothing but A intersection B complement. So the resultant membership function, which is A minus B of x, is nothing but A intersection B complement of x. Okay. Then disjunctive sum. There is something called as disjunctive sum. So which is A. It is represented by this particular symbol, A disjunctive sum B, which is nothing but A complement intersection B union A intersection B complement. Okay. So in this case, first we have to calculate A complement. A complement is nothing but 1 minus mu A of x, right? And then calculate the A complement intersection B. That is, take the smallest point of that two. Similarly, then calculate A intersection B complement. That is, first calculate B complement, which is 1 minus membership function of B with x, and then do A intersection B complement C, and then take the union of this, right? Then bounded sum. So bounded sum is given like this. That is mu A of x plus that is the bounded sum of B is equal to minimum of 1 comma mu A of x plus mu B of x. Okay. So uh, so what you have to do is you have to take, first you have to calculate uh, mu A of x plus mu B of x, right? So you have to, if you have two fuzzy sets A and B, you have to add both that, and you have to calculate mu A of x and plus B of x for all x1, x2, x3. I mean whatever the x values, and then you have to find out whatever the minimum. Minimum you have to compare with 1. Okay, and the resultant will be nothing but bounded sum. Okay, right? Say for example, the fuzzy set A is equal to, sorry, fuzzy set A is fuzzy set A is something like this: x1 comma zero point 0.2, x2 comma zero point 0.3. This is fuzzy set A. Okay, then fuzzy set B is, say, x1 comma zero point 0.3, x2 comma zero point 0.2. Okay, then first you have to calculate uh, the mu A of x plus mu B of x. Okay, so what will be mu A of x plus B of x? It is mu uh, A of x plus mu B of x. Okay, that you have to calculate. So that is nothing but you have to add these two. So zero point 0.2 plus 0.3 is 0.5. Okay, so there is uh, x1 comma 0.5. Similarly, x2 also 0.3 plus 0.2, x2 comma 0.5. Okay, so now then you have to calculate minimum of 1 comma mu A of x plus mu B of x. This is mu A of x plus mu B of x. Now the bounded sum will be what? It will be 1 minus minimum of 1 and this for every x. Okay, so for x1, if you take, is 1 is minimum or 0.5 is minimum? 0.5 is minimum, so we'll take x1 comma 0.5. For x2 also, if you take, which is minimum, 1 is minimum or 0.5 is minimum, 0.5 is minimum, so we'll take 0.5. Okay, right? So if somewhere if you get a value 1, then it will be 1. Okay, because anyway these values will not go beyond 1. So this is how the bounded sum is calculated. Similarly, next we have bounded difference. So bounded difference of two fuzzy sets A and B, or represented by this symbol. There is the membership function A of x minus, this is bounded, minus is bounded, B of x is max of, this is max of 0 0 comma, again you have to calculate the membership function of I mean you have to add the membership function value of A with the membership function value of B. After adding that 2, subtract that by minus 1. Okay, after adding that 2, subtract it by minus 1, and then you check the minimum of 0 and this one. So whichever the minimum, that we will be taking. Okay, so this is how the bounded difference is calculated. And then equality. Two fuzzy sets are said to be equal if their membership function produces same value. That is, if mu A of x is equal to mu B of x. Okay, that is, if you have a fuzzy set A, something like this, x1 comma 0.2 and x2 comma 0.5, and if you have another fuzzy set B, uh, with almost the same values like x1 comma zero point 0.2 and x2 comma zero point 0.5, then we say that these two fuzzy sets were same, equal. Okay. Power of a fuzzy set. So power of a fuzzy set, which is something like a power alpha. Already you have fuzzy set a, then the power of the fuzzy set can be calculated something like this, a power alpha. So the membership function is represented like this. Mu a power alpha of x is nothing but mu a of x, that is whatever the value of uh, the membership function of x to the power of alpha. Okay, because a, how we got a is nothing but the when you apply each x, you will get a, right? So for each x, now you, after applying the membership function, you take the power. Okay, so that is how we get a power alpha, right? Okay, so this is something which we have discussed already. If this alpha value is greater than 1, then that is called as concentration. If this alpha is less than 1, that is called as dilation. So normally we use this to extend the fuzzy set. Okay, so normally we use this to extend the fuzzy set, right? So, so this is how it works. Okay, next, Cartesian product. How to calculate the Cartesian product of two fuzzy sets. Say you have two fuzzy sets A and B. Now if you want to calculate the Cartesian set, Cartesian product, so there are two fuzzy sets A and B. But see, so far whatever we have discussed, in that case, both the fuzzy sets were working on the same universe of discourse. For example, A is also working on the universe of X, B is also working on the universe of X. In all the previous cases, that is the thing. Here, whatever we have discussed, two fuzzy sets A and B, both A and B are working on the same universe of discourse, which is X. Okay, but in case of Cartesian product, that is not the case. In all the previous cases, whatever we have discussed, both the fuzzy sets are working on the same universe X. But in case of Cartesian product, if you see, the two fuzzy sets are working on uh, different universe. Okay. For example, A is working on the universe X, universe of discourse X, and B is working on the universe of discourse Y. In that case, how will you calculate the Cartesian product? Okay. So Cartesian product can be calculated either for two sets belonging to the same universe of discourse, or they may also belong to different universe of discourse. So this is an example where two sets, they actually belong to different universe of discourse. That is, A belongs to the universe of X and B belongs to the universe of Y. Okay. So the membership function A cross B, which is the Cartesian product symbol, X comma Y is given as minimum of the membership function of A with the universe of discourse X and the membership function of B with the universe of discourse Y. Okay. So now, but how this should be calculated, in the sense it is little tricky. Okay. So it is calculated something like this. So you have to draw a matrix. Okay. So let us assume this is the set A and this is set B. So A contains four elements, x1, x2, x3 and x4 with the membership value, and B contains three elements, y1, y2, y3 with the membership value. Okay. So let us represent the A through the rows. So x1, x2, x3, x4, all these are represented through different rows, and B is represented through columns, y1, y2 and y3. Okay. Now what is it, the what is the rule says? It is minimum of the, what do you call, it is minimum of the membership value of A in the universe of X and the minimum of the membership value of B in the universe of Y. That is what you have to take. Okay. So first what you have to take is, you have to compare this x1 with y1. Out of this, which is minimum? 0.2 is minimum. So take 0.2 and write it here. Then again compare x1 with y2. Okay, x1 with y2. So when you compare this, what is minimum? 0.2 is minimum. So write 0.2 here. Then again compare x1 with y3. So which is minimum? 0.2. So write 0.2 here. Okay. So now x1 is done. Okay, x1 is done. Now go for x2. So compare x2 with y1, which is minimum 0.3 and 0.8. 0.3 is minimum. So write it here. Then compare x2 and y2, 0.3 and 0.6, which is minimum. 0.3 is minimum. So write it here. Then x2 and y3, which is both are same. So it is 0.3. right? So now x2 is done. Similarly, go for x3. So when you go for x3, compare x3 with y1. So what is minimum? 0.5 and 0.8. 0.5 is minimum. Then compare x3 with y2. 0.5 and 0.6. 0.5 is minimum. Then compare x3 and y3. Okay. So uh, what is minimum? 0.5 and 0.3. 0.3 is minimum. So write it here. Okay. Now x3 is done. Now proceed for x4. 0.6 and 0.8, which is minimum 0.6. x4 and y2, 0.6 and 0.6, both are same, so 0.6. x4 and y3, 0.6 and 0.3, 0.3 is minimum, so 0.3. So this is the resultant Cartesian product. So this is how we calculate the Cartesian product. Okay, right? So for Cartesian product, you have to draw a matrix and you have to do it. Fine. So like how there are other properties which are applicable for a normal set. Similarly, all those properties are applicable to a fuzzy set also. So for example, there is a commutative property which says that A union B is equal to B union A. So it applicable to fuzzy set also. So in a fuzzy set, if you perform A union B, it is equivalent to B union A. Okay. So if you recall, if two fuzzy sets A union B, if you want to perform, you will take the max points, right? Similarly, for A intersection B, it is similar as B intersection A. Similarly, the rule of associativity also applies. That is, A union B union C is same as A union B union C, and A intersection B intersection C is same as A intersection B intersection C. Okay, and the law of distributivity also applies. That is, A union B intersection C is same as A union B intersection A union C, and A intersection B union C is same as A intersection B union A intersection C. So all these rules are applicable for fuzzy sets also. Okay. Similarly, the rule of idempotence. A union A is nothing but A. That is, if you take two fuzzy sets and if you perform union, it is A. A intersection A is also A. It is not null. Okay. A intersection A is also A. That is, A intersection A is what it takes to. It takes the minimum point. So when you perform with itself A intersection A, you will get that 2 points will be same. So that itself is the minimum point. So that is nothing but A. A union null set is A. Okay. A union null set is A because the other set is empty. A intersection null set is also uh, A union null set is A because you take the maximum point, so it is A. Okay. A intersection null set is null. Okay, because the null set is an empty set, so we take that as the minimum one, right? And also the rule of transitivity applies. That is, if A is a subset of B, if A is a sub A, the fuzzy set A, if it is a subset of B, and the fuzzy set B is a subset of C, then we can say that A is also a subset of C. Okay. Similarly, the rule of involution also applies. That is there is a fuzzy set A. On that, if you perform A complement, and again over that, if you perform A complement, you will get A itself. Right? And De Morgan laws also apply. That is, A intersection B to the power of C. That is complement. It's not power. A intersection B complement is nothing but A complement union B complement. Right? Similarly, A union B, the whole complement is nothing but A complement intersection B complement. So all these rules of general, what you call, the linear algebra, it is applicable to the fuzzy sets also, right? With some changes. For example, in A intersection B, it is there it will be null set, but here it is A intersection A, it is A. Okay. So now let us discuss a few illustrations on fuzzy sets with some graphical representation. Okay. So let us consider two fuzzy sets A and B, right, which are defined over the universe of discourse X. Both A and B are defined over the same universe of discourse X. Say A is represented using the membership function mu A of X, and B is represented using the membership function mu B of X. Okay, then they can be graphically shown like this. Say this is the membership function corresponding to A. Okay, this is the membership function corresponding to A, and this is the membership function corresponding to B. Okay, now Now if you want to calculate A union B and A intersection B, how we will do that? That's what we are going to discuss. Okay. So to calculate A union B and A intersection B from this graph, it is better we combine these two graphs. Okay. So this is nothing but what you call this part is nothing but what? This is mu A of x. Okay. It is mu A of x, right? And the other one is this is nothing but uh, I'll take a different color. Yeah. So this is nothing but mu b of x. Okay. So this is mu b of x, right? This is mu a. Okay. This top one is mu a. This is mu b. Okay. Now if you want to perform a, if you want to perform a union a, what you will get? A union b. What you will get? So a union b means you want only the maximum point. Okay. From these 2 points, which is maximum, you will get this. Okay. You will get this, and then it will go like this, then it will come like this, it will come like this, right? This will be A union B, right? If you want to perform A intersection B, then what will be? It will be, you want the minimum point, so it will take this. Okay, it will take this and it will go this way, right? That is shown here. Okay, so uh, yeah, so this is A union B. So this part is nothing but A union B. That is from here it is taking the values from A, and here it is taking the values on B, right? And this is nothing but A intersection B. This is the resultant graph of A intersection B. Okay. This is mentioned wrongly. This is A. Okay, this is A and this is mu B. The brown color is A and green color is B as of the original graph, right? So you see here, this is A, right? This is B. Okay. So here also it should be that way, right? So this can be represented mathematically, I mean graphically, that's what we are discussing here. So similarly, if you have a fuzzy set A, its complement, you can also draw mathematically. I mean, you can also draw it graphically. So if this is mu A of x, then what will be mu A dash of x? It will be just reverse. For these lines, for this point, actually it is 1, so it will give 0. So it will be something like this. Okay. So this is the resultant one, which is nothing but mu A dash of x. Okay. Or mu complement of x, whatever you can call it as, right? Okay. So you can try this for these functions. You can try plotting a graph. Okay. Consider the following two fuzzy sets A and B defined over the universe of discourse 0 to 5. Okay. So that is you can take different x values. So x values, this you can try as a homework. That is x, you can take values from 0 to 5. 0, 1, 2, 3, 4 and 5. Okay. Then you calculate what is mu A of x. Okay, mu A of x, you apply this formula. X by 1 plus x. Okay, that is 0 by 0, 0 by 1. Okay. So 0 by 1 is nothing but 0, right? So that is what? When x is 0, you are getting the value 0, right? Similarly 1, when x is 1, what you are getting? 1 by 1 plus 1, it is 1 by 2, which is when x is 1, you are getting 0.5. Like that you calculate, right? Similarly, you calculate for mu b of x. So mu b of x you apply on this formula, 2 to the power minus 0. Okay, 2 to the power 0 is nothing but 1. Okay, so 0 comma 1, then 2 to the power minus 1. Okay, uh, what is that? You calculate, right? So on and so forth. You calculate all the values, right? And for this, you can, for this what you call, you calculate these values, and then you can try to represent this mu A of x as a graph. and represent this mu a of x as a graph and represent this mu b of x as a graph, and you can calculate a union b, a intersection b, all these things, a union b complement. You can also calculate a complement and b complement. This you can take it as a homework and you can try, right? Okay, so here is another example. Say, let us say there are two fuzzy sets A and B with membership function mu A of x and mu B of x. Say A represents the cold climate, that is the membership function A represents the cold climate and the membership function B represents the hot climate. Okay, so the membership function A is given like this. This is the membership function corresponding to A. This is the x represents the temperature. That is when the temperature is -15, -10, -5, 0 up to 5. It is giving 1 for cold. It is very cold, right, during that time, right? Similarly, when the membership function is more than, that is when x or the temperature value is greater than 25, 30, 35, 40, 45, it is giving a value of 0 because it is not cold at all. It is not cold, right? But for hot, if you see, when the temperature is -15, -10, -5, 0 or 5, it is giving a value as 0 because it is not hot. And when the x value is greater than, when the temperature is greater than 25, 30, 35 or 40, 45, it gives the value 1 because it is hot, right? So this is the membership function corresponding to cold climate and this is the membership function corresponding to hot climate. Okay, so this is that x is x being the inverse of this course here, which it represents the temperature. So this is the range of temperature -15 to +50. Now we can, from we have only two climates, we have only two membership function, cold climate and hot climate. From this we can derive different membership function. Something we can derive not cold climate, we can derive not hot climate, we can also derive extreme climate, and also we can derive uh, uh, pleasant climate. Okay, all these things we can derive, right? So for example, what is not cold climate? So not cold climate is nothing but 1 minus mu a of x. It is the inverse of the cold climate. Okay, so not cold climate is nothing but 1 minus the cold climate, and not hot climate is nothing but 1 minus the hot climate. Okay, it is the inverse of the hot climate, right? So uh, so for example, say, so A represents what? A represents cold climate, right? A represents cold climate and B represents hot climate. Okay. So for hot climate, if you see, when the temperature is 15, -15, when the temperature is -15, it gives 0. Okay. So when you do 1 minus 0, you get 1. Okay. Right. Okay. So right. So like that. So similarly for cold climate, when the temperature is 15, it gives 1. Okay. So then you have to do 1 minus 1, that is 0, right? So like this you calculate. So not cold climate is nothing but 1 minus cold climate. Okay. And not hot climate is nothing but 1 minus hot climate, that is 1 minus membership function of x. And extreme climate can be calculated like this, A union B. Extreme climate can be calculated like this, A union B, which is the membership function of A union B of x, which is max of the membership function of x and the membership function of A and the membership function of B. Similarly, the pleasant climate can be calculated like this. It is A intersection B, which is minimum of the membership function of A and the membership function of B. Okay. So hot climate, so the extreme climate, what you will get is, it is the maximum point of these two, so you will get this as the extreme climate. Okay, so the resultant graph is this. Okay, whereas the pleasant climate, you will get this as the pleasant climate. Okay, so you got this as the pleasant climate, right? Okay, so here we are deriving more membership function from existing membership function. Initially we had only two membership function, one corresponding to cold climate Okay, and another one corresponding to hot climate. From this we derived these membership functions like not cold, not hot, extreme, and pleasant. Right? Okay, so that's it. Let us stop here. Fine. Thank you.